Math 2414, representing functions as power series, video 6. I think it's 6. 1, 2, 3, 4, 5, 6. Yes, video 6. Differentiation and integration of power series. We're getting to the end of this section soon. It explains why we're doing all of this. Spoiler alert, because not all functions are integrable, but all polynomials are. Suppose we have a power series for f of x centered at A with the radius of convergence of R. Centered at A, excuse me, it's not what I meant to happen. Centered at A with the radius of convergence of R. In other words, suppose f of x is equal to this sum, the sum from n equals 0 to infinity of Cn times x minus a to the n, since we're centered at A, on some interval a minus r to a plus r. And remember, that makes perfect sense because the middle of that is a, and we go r in both directions. A minus r takes you to the left, a plus r takes you to the right. So let's say we have a power series that converges on this open interval. Now, it may also converge at the endpoints. In other words, we may have convergence here or we may have convergence here, but we're just assuming that we have convergence in the middle of the interval when we have a given center and a given radius. If our function is defined as a power series with a particular interval of the convergence, then our function is differentiable and continuous, which means we can take its derivatives and its integrals, and more specifically, the derivative with respect to x of our function is equal to the sum of the derivatives of the individual terms. And we can actually take the derivative by bringing down the power in front of the coefficient and then lowering the power by 1. So in other words, all this is saying is we can take the derivative of a power series term by term, and we can take the integral of that power series term by term. The integral of the f of x is equal to the sum n equals 0 to infinity of the integral of Cn times x minus a to the n dx. So we can integrate term by term, but we can actually integrate this thing. To integrate it, all we have to do is raise the power by 1 and divide by the new power. So Cn over n plus 1 times x to the n plus 1 plus a constant because it is an indefinite integral. So basically that's all this is saying. Well, it's not all it's saying, but it's the key thing it's saying, is that if you have a function defined as a power series that converges on some interval of convergence, then the derivative of the function is the sum of the derivatives terms, the sum of the derivatives of the derivative of the function is equal to the sum of the derivatives of the individual terms of the series, and the integral of the function is equal to the sum of the integrals of the individual terms plus c. And I said that's mostly what this says. It says a little bit more, so we'll just type it over here. Additionally, both the derivative and integral converge on the same interval of convergence, except possibly at the endpoints, which must be checked individually. Let me widen this text box. So what this means is when we take the derivative of a power function to get a new power function, or the integral of a power function to get a new power function, the interval of convergence has the same center and the same radius. So it starts in the middle and goes out the same amount. The only thing that might change is whether or not you pick up convergence or lose convergence on one of the endpoints of the interval. So that's all it's saying. I thought about doing an example in the midst of this, but I wanted to get this idea out there first. We'll do some examples in the next videos. All this is really saying is for a power series, you can take the derivative and not lose convergence, except possibly at the endpoints of the interval. And you can take the antiderivative, the integral, and not lose convergence, except possibly at the endpoints, where you could also gain convergence. We'll take a look at several examples of using this to generate power series for new functions.